Hello everyone, this is Dr. Yuzo, and today is our third lecture in ECE 360. Can you guys first of all hear me well? And also being able to see my screen here? Any trouble? Everything's good? Thank you Zach. Thank you Turkey. Thank you too. All right, let's start then. Here, first of all, I'm trying to summarize what we have learned and as well as what we will learn actually in this particular module, module 2. Okay, module 2, the frequency domain modeling. And last lecture, we basically provided the overall picture of this module, which is talking about, we're beginning with the physical system or say component. Okay, generally speaking, they're what? They're either mechanical or electrical, okay? Either mechanical or electrical components or subsystems. And then based on the physics principles, okay, based on physics principles, you might learn from physics class or any other classes, we come up with the differential equations. Okay, this is obviously math work. Based on this differential equation, we can play back and forth with the S function or say the transfer function. Okay. Transfer function TF is the term we will use a lot of more often. Okay, so transfer function and the differential equation. Okay, two things. Okay, obviously one is the time domain. Obviously this is time domain. Okay, whenever you just have correct understanding, this is time domain. Okay? This is nothing but time domain. And then transfer function obviously is frequency domain. Okay, frequency domain. Because our title, module 2 title is frequency domain modeling. Modeling, what is it? Just a frequency domain transfer function, okay? In terms of S. Time domain differential equation in terms of time t makes perfect sense. So as I said, back and forth meaning conducting Laplace transform and reversely the inverse Laplace transform, right? Two things, okay, back and forth, right? So if we move on, second one we're gonna learn is actually just how to conduct this Laplace and the inverse Laplace transform. First, one way is from the differential equation to the transfer function. Okay. Assuming a transfer function, assuming differential equation is given, and then how we come up with the corresponding transfer function in frequency domain. What we will do, or actually we have partially done this in the last lecture. What we need is a handout. Okay, which handout? The Laplace serial, because we had two handouts. One is table, and another is serial. We are using the second one, the serial. And the number 9, if I remember correctly, the number 9 in this handout is this. Okay, is this, which is saying the nth order derivative of a function f of t in time domain. Okay, if we are conducting a Laplace transform on it, bracket capital L, it equals to s to the n times capital F of s. Obviously, this is the transfer function, or say this entire thing is transfer function, but f of s is what? F of s is equal to Laplace transform of f of t, lowercase f of t. Okay, this is the correct understanding. Capital F of s is the Laplace transform result of the lower f of t. In other words, time domain function f of t, whatever it is, the corresponding frequency domain transfer function is capital F of s. Does it make sense? Based on this black thing, we are developing further to this derivative. Okay, derivative. If you have an nth order derivative at lower cap f of t with respect to time t, the Laplace transform result, or say the corresponding transfer function of this derivative, is equal to s to the n times capital F of s. Right? And of course, minus bench of the summation of a bench of initial values. And the most of the time, initial value assumes to be 0. Okay, most of the time, except otherwise being told. We can assume initial values to be 0, except otherwise being told. Okay, and this is how we understand this formula in one of our handouts. Okay, and if you go through example to see, it's not very difficult. Just being careful enough, then you get a full credit in the exam. Okay. And third thing we haven't touched yet, but is obviously very predictable. It's the other way around, which means given transfer function, how we find out the time domain differential equation. And then what if you do? Probably you guys learn something like this in other ECE course. We're going to do partial fraction. Okay, partial fraction. And then from the partial fraction results, we go back to another handout, which is the table, to find out the differential equation results. Okay, we will see how it works in that way. Okay. And now let's continue our lecture. So this is where we ended last time. Okay, this is where we ended pretty much 1 week ago. Okay, and first of all, lowercase r of t is input, lowercase c of t is output. According to this definition, we conduct the Laplace transform based on, again, this formula, based on this formula. And then we come up with this pretty much equation in terms of capital C of S and the capital R of S. What we're really looking for is a transfer function. And once again, what does it mean by transfer function? Transfer function is output divided by input. Okay, that's a very, very important concept. Transfer function of a component or system equals to what? Simply output over input. Output, according to the definition here, is C. Therefore, in S domain, this is a capital C of S. Input is whom? Input is R, defined by here at the beginning here. So over capital R of S. Output over input equals to the transfer function of this system or say component. We can give a name, whatever T or H of S is the transfer function name. Okay, and then you apply a kind of a math, and then you end up with the numerator as S polynomial, mth order. Denominator is S polynomial as well, with nth order. Okay, with a bunch of coefficients of B's and A's in numerator and denominator respectively. Right? This is a little bit of math. Okay, this is a bit of math. In other words, in the left-hand side of the equation here, the left-hand side of equal here, we extract capital C of S out and then left bunch of A's coefficient, sum of them, and do the same thing to the right-hand side of the equal. And then you organize them into a format like this. Okay, so this is how we come up with the transfer function. Yes, you need to be careful. Defining at the beginning, definition of the at the beginning for input and output, or say which is which, who is whom, is very important. Okay, very important, because it's determining who gonna be the numerator and who gonna be the denominator. Okay, right. So according to which, let's move on to a example. To example. Give a specific differential equation. Given a specific differential equation. Okay. what you see is two variables, right? Two variables, y and x. Obviously, one is input, the other is the output, and both are function of t. What I'm saying is y is meaning y of t, x meaning x of t. Okay, both are function of t. Therefore, you are seeing the derivative of them with respect to t. Does it make sense? So this is the differential equation that we are having at the first place, and then trying to conduct the Laplace transform on it, and then have the transfer function. So here, if we are defining input as x of t, output as y of t, and also assuming all initial values are 0.
So why is it in specific that we specify our initial conditions as 0? Is there a reason that we just assume?
We just assume. We just assume. Because trust me, if involving initial condition into the picture, everything gonna become much more complicated. So as we learning this at the beginning, we are assuming the easiest case, which is 0 initial conditions, which is obviously not necessary. Okay, which is not necessary. We just assume. Is that all right, John?
For now, sure.
Yep. For now, sure. If you involve the initial conditions, this formula should involve this part, which is constant, not 0. Okay. All right. How about let's just do, because again, looking at this differential equation, we are seeing many individual derivative and the sum of them. So we can do Laplace transform on them individually, right? Let's do one. Let's just do this one, and then leave the rest of them for yourself to do in-class exercise. So third order derivative of y of t with respect to t's cube here. The corresponding Laplace transform result is s cube times y of s. Lowercase y becomes capital, and of t becomes of s. Right. This is the Laplace transform result for the first term. For the rest of the term, you guys spend maybe 1 or 2 minutes to proceed. And then according to the defined input and output, find out the transfer function. Okay. Find transfer function in S domain, or say frequency domain. So totally give you guys 3 minutes. Okay. And come back, I will present the solution. Okay. So talk to you guys in 3 minutes. Right. Come up with the transfer function. Okay. Conduct the Laplace transform on each term first, and then organize the resulted equation into a transfer function format. Okay. Like what we did here. And you can imagine, well, obviously, the resultant transfer function is supposed to be a polynomial divided by another S polynomial, right? All right. Go ahead. right, guys, let's see the solution here. Okay. So second term is obviously we cannot lose the coefficient of 3. 3s squared capital Y of S plus 7s Y of S plus 5y of S equals to the right-hand side of equals to S squared capital X of S plus 4x of S plus 3x of S. Of course, here we have S here, right? 4s x of S. 4s x of S. And then transfer function. And again, once again, be very careful who is the input, who is output, because the transfer function equals to output again of S over input of S. So identify them respectively as capital Y of S and X of S, right? And then what matter is just organized, and then your numerator polynomial of S supposed to be the coefficient of X of S in the equation. Therefore, it's S squared plus 4S plus 3, right? Denominator are the S polynomial as coefficient of capital Y of S. So S cubed 3s squared plus 7s plus 5, right? So this is the result. That's the correct result. Are there any questions, any concerns? Anything? All right, we can move on. Is that backwards? I had numerator and denominator flipped.
I have a question.
Hold on. I first of all, I received Alex's question. He saying, is it flipped? I don't think so. It's not flipped. It's again, a numerator is the coefficient times to the x. Therefore, is this guy, right? This guy, this part. Denominator or the polynomial times onto the y of s. So this is so. Yeah. The coefficient of x supposed to be on the top. Yes, because your x is input, which is denominator, right? That makes sense. Anyone got the same or say anyone get the flipped or any comments? Any comments?
Yes, I am confusing the same thing. Like you put x of s in denominator and y of s in numerator. I just confused over there.
Let me ask you this question. Let me ask you guys this question. So from here, go back to this equation above it. What are you going to do? Numerator here times onto the denominator polynomial, right? Am I right? Equals to x here times the numerator here. Exactly same as this equation. Does it make sense?
Yes, yes.
What I'm saying is try to go from here back to the given differential equation, okay, to see if you can get there.
Hello?
Yep.
So it looks like you pull out the y of s's and the x of s's. How can you just pull those out?
Oh, details are like this. So we start from this equation, obviously, and here you got it's like this, right?
Yep.
This is what you got from here, the left-hand side of the equation, right? Because everything is times the y of s. So you take the y of s out as the common factor. and then leave the s terms left as this. And then do the same thing on the right-hand side, x of s, and then times s polynomial as this. Okay. And then from here, you keep moving. Well, actually, you can end up with this.
Okay, never mind. I see what I don't know why I didn't get that. Thank you.
Yep, sure, no problem. And again, be very careful. Once you got this equation, once you got here, be very careful. Who is dividing whom? Okay, it's up to how you define input and output. It has to be output over input. Output must be y, okay, on the numerator. Input must be x in the denominator. Has to be like this. Okay. Well, sometimes you can save the parentheses of s. Keep the capital letters over there. That's fair enough. Okay, so you can have y over x without of s. That's fine. However, the numerator denominator cannot be flipped. Okay, so once you do this, and x times the numerator here is this equation here, this polynomial here. That's why this guy go to here, this guy go down to here. And then which is our previous solution here. Okay. Any other questions? All right, if this is clear, just one more reminding you guys, be very careful, okay? And look at here, this equation. You have a third order derivative, second order, first order, and zero order, right? 3, 2, 1, 0. Very nice, very nice. The other hand side of the equal is the second order, first order, and zero order. Very nice too. 2, 1, 0. 3, 2, 1, 0, and 2, 1, 0. Very nice, right? Be very careful. If one is missing, it's very easy to make mistake. Okay. So say you don't have this term. It's very easy to make a mistake. So you need to be very, very careful. Okay. So the order of the derivative must be the order of the s term. They must be same. Okay. Order of derivative must be the order of s term. Order of this derivative is 1, correspondingly s term, the order is 1, 2. The derivative order is 0. And then s term here, the is 0, 2, right? That's why you end up with 1, just the 5 itself. Okay, be very careful on this. Okay. All right, we can move on. Due to the time, we don't have a chance to do second example, but this one is very involving, so should be good. Should be good. All right. Now let's talk about the third thing. As we have mentioned, it's about the other way around, from the given transfer function back to the differential equation. Okay, from frequency domain, or say s domain, same thing, back to the time domain, differential equation. Okay, the other way around. Earlier I mentioned what we're gonna do is this. Okay. We're pretty much gonna do partial fraction. After having the partial fraction results, we're gonna go to the handout, the Laplace table, to conduct the inverse Laplace transfer. Okay, to conduct the inverse Laplace transfer. Okay. All right, let's see. So first of all, transfer function, the given one, might be in two different alternative formats. Okay, one is called the ratio of two polynomials. This is the one we saw from previous section. Okay. Pretty much numerator is polynomial of s with the highest order of m. The denominator is another s polynomial with the highest order of n. Okay, they of course they're likely to have different coefficients, b's and n's. That doesn't matter. Division between two s polynomials. Alternatively, we might have another format to describe or say to write the exactly same transfer function, which is called zero pole gain, okay, which in which you have a numerator here, capital K as constant gain, times parentheses s minus z1 times second parenthesis, in which have s minus z2, and then times so on and so forth. Okay, you might have many z's over there. Denominator, similarly, you have s minus p1 times s minus p2, and so on and so forth. The product among many s. Okay. So look at these two formats. The first format might makes more sense or easier to understand of the second one. The second one, again, it's alternative. Okay, it's alternative, which means exactly same. These two are exactly same one. The only thing is you are kind of organize the numerator and the denominator respectively into a product among different first order S term. From here, what we can tell here is this. Yeah, we can tell here is this. We call the roots of the numerator as zeros. We call the roots of the denominator as poles. And obviously, the roots of the numerator is also the roots of the numerator here, because again, they're exactly same. Okay? And the denominator here, the roots are exactly the roots of this polynomial here. Again, exactly same. But from the second format, we can easily tell who are the zeros, who are the poles. In other words, who are the roots of the numerator and who are the roots of the denominator. Okay, much easier, isn't it? So zeros here are what? Z1, Z2, and a bunch of Z's left here, right? Who are the poles? P1, P2, and so on. Okay, down here. Okay, we can easily tell that. Of course, be careful here. Okay, if you're seeing the plus in the numerator or plus in denominator, then the corresponding zeros are what? Negative Z1, right? Does it make sense? If here is positive here, it's S plus Z1, and then who is the zero? Negative Z1. Okay, be very careful here. Once again, zeros means the S value making numerator equal 0, which means nothing but the roots of the numerator polynomial. Similarly, what I mean by poles means S value making denominator equal 0, which means nothing but the roots of the denominator. Does it make sense? So these are the concepts of zeros and the poles. Two very important concepts we will use in future for controller design. But we first time bring it up for now. Okay, two formats. Again, they're the same, alternative. And now let's talk about our partial fraction. Okay, partial fraction. First of all, which class you guys learned the partial fraction by the first time? Please don't tell me you can't hear me. Okay, good, very good. That's the only thing I really fear. But Calc 2, okay, good. That's fair. Okay. To be honest, the partial fraction could be very complicated. Okay, it could be very complicated. However, in this class, especially in the exam, I'm not planning to assess any complicated ones. Okay, the complicated ones and some tricky ones can left to what? MATLAB. Okay, I will today teach you guys how to use the MATLAB to conduct the partial fraction. Okay, and that's the tool you always use for a complicated problem. Okay, in the exam or homework exercise, we just focus on some basic concepts. Therefore, no complicated ones. Okay. And partial fraction, since basically everybody know what it means. So let's just do a couple of examples here as review. Okay, and nothing is better than examples as review. Okay, very simple. Given the transfer function or say a S domain model, capital F of S, equals to 2 divided by S plus 1 times S plus 2. Obviously, this is zero-pole gain format like this, right? Format is easier for us to conduct the partial fraction. That's why we begin with it. How to conduct the partial fraction? Okay, how to conduct this? You're seeing two parentheses product in the denominator, right? You might have different way, but my way is like this. Immediately, I assume the given transfer function equals this, equals to the summation of two fractions. First fraction has constant gain of k1. Second has constant gain of k2 in the numerator. Right? Denominator is respectively s plus 1 and s plus 2 as the according to the given product here. Okay. And then the rest of the thing just algebra. Okay. Remaining equal. Okay. Always remember equal. We are talking about the same thing. Okay. I really conducted the summation between these two. The numerator is gonna be this guy times this guy, right? The numerator, the denominator is gonna be s plus 1 times s plus 2. The numerator is gonna be what? Going to be k1 times s plus 2 times k2 times s plus 1. Does this make sense? Or is it same as what you guys learned before? If so, we can move on. What you need to do next is just expanding the numerator into this format. Into the S polynomial with coefficients in terms of k1 and the k2. Does this make sense? Because the k1 times s is k1s, k2 times s, k2s, and then you combine them together is k1 plus k2 times s, right? Constant term gonna be 2k1 plus 1k2, like this. So s term, constant term. And then it's time to move on. Time to move this up. So again, once again, this is equal, right? Which means this guy and this guy, these two circles are exactly same thing. And by closed loop, we're seeing the numerator are identical. Numerator identical. Then what does it mean? It means the denominator identical. I'm sorry. Denominators are identical. What matters is since they're equal, the numerator must be same as well. This is the conclusion we can easily have. Denominator identical. Okay, numerator must be same as well, right? That's again same. Two circles are same. And then what we need to do, just observe the s term and the constant term. On the left-hand side of the equal, we only have constant term too, without any s term. In other words, s term on right-hand side here is what? 0. Okay. Otherwise, it couldn't be equal because left-hand side, again, there's no s term, only constant term. Therefore, the right-hand side of the equation, right-hand side of the equal, s term must be 0. Therefore, the constant coefficient k1 plus k2 must be 0. Okay. And meantime, constant term equals to constant term. And then what do we got from here? K1 and K2 value. We got them. We got the constant term. Because two equations, two unknowns, right? Save time, we just directly have the answer here. Positive and negative 2. That's K1 and K2. And further, what we got? The given transfer function capital F of S is just equals to what? S plus 1 numerator is 2 plus 92 over S plus 2, right? This is the partial fraction result. The first step done. The partial fraction is done. Okay. We're not done yet because this example is find what? Find the time domain differential equation, right? Differential equation. Right? It's like this. Then the next thing is conducting the inverse Laplace transform by utilizing the table we have. All right. Next, inverse Laplace transform. Anything, Mohammed? Any questions?
So I got a question. When we're, instead of like doing the partial fraction decomposition, if we use the, I guess it is still partial fraction, but if we use the shorthand method, you know, where we multiply by a pole and then just add the inverse when solving.
No problem. No problem.
Okay.
Yeah.
And then the second thing I had was, are we allowed to use the cosine expression instead of the cosine for the second order differential equation poles?
Cosine what instead of cosine?
Like if we have a second order differential equation as a pole, if we use that and expand it to complex, can we do that instead of doing the secondary, you know, where it gives us a cosine and a sine? Instead, we do a complex pole, which gives us just a cosine with a phase shift. Is that acceptable?
That's fine, actually, but the truth is I'm not planning to ask you guys to conduct anything like that in the exam. So I'm not expecting for you to see that problem in the exam at all. But the answer is yes, feel free.
Okay.
So the answer to both of your questions, yes, feel free. It's how you conduct it that doesn't matter, because pretty much what I have done here is pretty much kind of a review. If you have learned or have quite familiar with something different, then feel free to apply. I don't mind. It should be fine. Okay. And then and now's the time for us to go to your handout. Yep, this is the best of you. This is the best of you we can have. Right here. So this result to this result. Now keep in mind this is the result. And then conduct the inverse Laplace transform. And then obviously we're gonna go to the table here. The table, which formula we should use? Obviously this one, right? Doesn't make sense. This one. Numerator 1, constant, whatever. And denominator is S minus A. Be careful, it's S minus A, not plus A, okay? And the corresponding inverse Laplace transform result is e to the A positive A t. Lucas, can you mute? Thank you. Okay. E to the positive A times t, all right? It sounds like that way. Yeah, I agree with you, Jeff. Anyways, so again, minus A here, positive A here. Okay, be very careful. So correspondingly, again, I gave you guys 1 minute. What is the Laplace transform result of these two terms? Keep the plus in the middle. We don't need to touch this guy. You just respectively conduct the inverse Laplace transform to these two terms, right? And then keep the plus in the middle, right? one or 2 minutes or so. Please go ahead. Yeah, Dev, it's your turn to mute.
But no, I'm going to say answer. Can I say it?
I'm sorry, what?
I'm gonna say the answer. Can I say what gonna be there?
Oh, I'm gonna present the answer here. If you're
Oh.
done with this, just wait for my answer, for my solution.
Okay. Thank you.
Sure. Right here. The answer obviously is 2 times e to the negative t plus in the middle and negative 2 times e to the negative 2t, right? This is the answer for this inverse Laplace transform, right? So, okay, pretty much this is the answer. Okay. Frequency domain transfer function f of s is equal to, or say equivalent to time domain. The corresponding time domain expression is like this, right? Any questions before we go ahead for second example? Let me leave a little bit more time for you guys to conduct the example 2 independently. Okay. Again, find the time domain expression or another transfer function f of s equals to this. Well, almost the same thing. The only difference is what? The only difference is this square, is the existence of this square. Let's begin the first step together. Let's begin the first steps together. How to conduct the partial fraction on this guy? We still need to split this product in the denominator into the sum between multiple fractions, right? But how to split it?
You would have 3 constants instead of 2.
Exactly, 3. Which 3?
S plus 2 and then another s plus 2 for the denominator.
I think not exactly right, but here is the answer. Is this what you said? Maybe I missed. Maybe I misunderstood you.
No,
The key is, yep. The key is the third term here. The denominator is square. Okay, be very careful here. You need to keep the square over there. So this is how you split this. The first step. So if this is fine, then just go ahead. Let's see the solution back in like 5 minutes. Okay, 5 minutes, and I leave the table over here as your reference. So go ahead. Talk to you guys in about 5 minutes. And if you're done with the partial fraction, feel free to move forward to conduct the inverse Laplace transform. Okay, 2 steps, remember. Have you present the solution momentarily? All right, here are the results and the procedure for the partial fraction. And as we earlier mentioned, the key is here. Remember, the third fraction is supposed to be k3 divided by s plus 2 squared, s plus 2 squared. And then therefore you sum these three fractions together, sum them up, ending up with as polynomial in the numerator, of course, in terms of k1 and the k2 as the coefficients. And you compare to the original polynomial of s, which is just a constant term s. I'm sorry, constant term 2. Okay, and there's no s term at all. Therefore, you can tell the coefficient of s squared term is 0. The coefficient of s term is 0 as well. And the constant term equals the constant term here too. Okay. This is how you end up with the 3 equations and 3 unknowns. Okay, you got the algebra result, 2, -2, and -2. Okay. And then further, f of s just equals to obviously 2s plus 1 plus -2s plus 2.
Professor,
Yep.
I might be a little rusty. Can you explain again how you came up with the 3 equations?
3 equations. Okay, here. Now let me use the red. Here. How about this one? Is this one okay, or?
Honestly, I was trying to figure out how you came up with that you highlighted with the red.
Okay.
Or circle.
So from this step to here, pretty much from this step to here, right? So how we come up with this? You have 3 denominators. You have the product of them, and then respectively here is what? K1 times what? S plus 2 times s plus 2 squared. This is the first term becomes. And then it equals to the second one, k2 times s plus 1 times s plus 2. Then denominator is s plus 1 times s plus 2 squared. This is second term, right? And plus the third term, this guy is equals to what? S plus 1, s plus 2 squared. Numerator is k3 times s plus 1. Okay, so this is how we come up with this. Okay, sorry. This equation here is equals to this equation. Okay. If this makes sense, then this is further equals to here. Okay. So this red color, I'm writing in red. This is the middle step between this step and this. Between this and this. Is that better?
Okay, that's a lot better.
Yep. Thank you. All right. So this middle step, and then further by conducting the inverse Laplace transform, which means we need to go to this table, and then f of t just equals to, let's see, 2 to the negative t minus 2 equals to negative 2t here, plus, say, minus 2 t e 2 t negative. There. Go here, let's go here, let's go here. 2 times e to the negative t minus 2 times e to the negative 2t minus 2 times t times e to the negative 2t. Yeah, I think the answer here are correct. Correct. Good. So any questions regarding this before we move on to learn how to do this in the MATLAB? Any questions? Again, I'm not planning to give any overcomplicated partial fraction in the exam. So you just need to understand the basic procedure like this. Okay. Any questions? Yeah. All right, let's move on. Let's move on here. Here, this is number 6. Obviously, we have number 1 through 5. We will see if we have time today to talk about them. But this partial fraction is the most important thing for today. Okay. So here is teaching you how to conduct a partial fraction to a given transfer function like this example here. Okay. Like this example here. So first of all, the command is called residue. What does it mean by residue? Residue is like something divided by something and then remainder, right? Looking for the remainder. So not surprised that is numerator, who is the one on the top, divided by the denominator, who is on the bottom, right? So 2 arguments in the parentheses. First one is numerator, remember. Second one is denominator. Okay. And then the return results are 3 things. Okay, the return results are 3 things. The point is you're going to see 3 values, which is not directly the results we are happy with. The summation of 3 or 2 multiple of fractions. No, it's not like that. Not yet. You have to learn how to interpret those 3 results. So 2 things, how to use this command to come up with 3 values. Another is how to interpret these 3 values so that you're able to translate it to the partial fraction results. And here's some explanation. For R is the residues of the partial fraction expression. Second one, the P result is poles of the partial fraction. K is the direct term. Okay. By reading these definitions, we know nothing at all. Okay. Until we see this example. So first of all, how to do this? So numerator is a polynomial of S, denominator as well, right? So how to input the polynomial of the numerator? Here we are defining the numerator, which is obviously the output as B. Output as polynomial is equal to 94, which is the coefficient of S term, and 8, space 8. 8 is the constant. Okay, this is how you input a polynomial of S. You learn that from, because again, we have 1 through 5 before the 6. So this is how to input this polynomial was taught there. But here, 94, 8 means 94S plus 8, polynomial of S. Similar to the denominator A, which is the input. Another S polynomial. How to input it? Coefficient of highest S term, highest order S term is 1. The second highest S term coefficient is 6. And the last, the constant term is 8. 6, 8. 1 space 6 space 8. This is how you input this second denominator as polynomial. According to the command here, we learned the syntax here. So the RPK equals to bracket RPK equals to the residue of the numerator, comma, denominator. As simple like that. So you need to know how to input a polynomial and then correctly identify who is numerator, who is denominator, and then you're done. MATLAB going to return these as results. MATLAB going to return these as results. which, as I said, is not the partial fraction result. We have to correctly say being able to translate this into the partial fraction result. Okay. By watching the translation, let's go back to try to interpret it. The denominator, the given transfer function, the highest order is 2. Therefore, is sum of 2 fractions. It makes sense. First fraction, look at the numerator, which is obviously constant, right? -12. Here, okay. Results of R. The first result of R. Second constant 8 is second result of R. And then the P is the pole value. The first pole is 94. Second is -2. Those are the value as values making the denominator equals to 0. Therefore, the first denominator here is s plus 4, not -4. Second is s plus 2, since -4 and -2 are the s values, making them equals to 0, right? So poles value contained inside of P.
Will MATLAB explain those poles in complex when they're complex, or no? Do they not behave that way?
They will. They
Okay.
will.
Okay.
They
Cool.
will. They will. They will. Yes, they might be complex. Absolutely possible. Absolutely possible. K, direct term, which is empty, right? This is nothing. Okay, this is empty. What does it mean by empty? Anyone can have a guess? In other words, if K here is not empty, it's something like let's say 1, constant 1. Not only 1, but what I mean is 1. If K equals 1, then where is K here? This is obviously the key, right? K equals 1. Then how we have the 1 here? Where is the 1?
That would be a steady state solution, shouldn't it? So, or sorry, it's non-transient, so it'd be a plus. You just add whatever K was to
Good. Very
partial
good.
fraction.
Very good. Okay. So if K here equals 1, then the result is going to be what? Plus 1 term, which is plus 1. That's it. Direct term. Call it direct term.
Wouldn't it be 1 over S if we're still in Laplace? Because if the end result is supposed to be a constant value.
The thing is, let's assume this. Let's assume John's assumption. Let's assume I'm sorry about this. It's very hard to sketch clearly. But let's assume the correct result is this guy plus 1 over S. Then going back to the RPK, what they supposed to be then? R, first of all, equals what? -12, 8, and what? 1. Does it make sense? 3 terms. And then correspondingly, P equals what? -4, -2, and what? 0. Does it make sense, guys? And the K remains as what? Empty. Does it make sense? 3 terms, okay, 3 entries in R and P respectively. Right? Because 1 over S, look at that, 1 over S, the poles of 1 over S is what? 0. That's why here is 0.
Okay.
Yep. Any other concerns or questions?
And the K value would be like, let's say S squared was multiplied by 2 as a coefficient. If we pulled a 2 out from that, then it would be, S squared plus 3S plus 4. But that 2 that we pulled out, it would be plus 2 as K. Is that what they're saying?
Not quite follow you.
Like if there was a 2 in front of the S squared and we pulled out 2 from the whole denominator, would
You
that
mean
2
you have
either
a 2 here, right?
in front of s
You-
squared, multiply, so 2 multiplied by s squared in the denominator, the s squared.
That's what I'm writing here, right?
Oh,
2 times
sorry, I
s
was looking
squared.
at the other one. Okay, yeah. If we pulled 2 out, would that, obviously be s squared plus 3s, and that would change the poles there. But
No. If you have 2 here, guys, be very careful. If you have 2 here, you can put 2 out in the denominator. That leaves 2 times parentheses s squared plus 3s plus 4, right?
yeah,
And then John's concern is what we do to this case. In this case, be very careful, everybody. This denominator 2 is considered as what? Constant gain in the numerator, 1 over 2. This is the right way to deal with it. Okay? So pull this 2 in the denominator out to write it onto the numerator as 1 over 2. Okay? This will avoid any confusing.
and that
Right
1
after.
over 2 would be,
Constant.
that would be the
Constant.
k, correct? The gain, right?
Yes.
Oh, okay.
Correct.
I see where that
Correct.
comes from. Okay.
Okay, but not this k. Okay, don't be confused with this k. This 1 over 2 is the k we learned from the notes, the zero pole gain format. That k. Okay.
So I'm just kind of confused. How would we ever get that plus a constant then if it's not that gain? Like, what
No,
does our equation need?
That's absolutely possible. That's absolutely possible. For example, you have, well, again, 1 over 2 as gain, and the numerator has a parenthesis, which is exactly same as this parenthesis, s squared plus 3s plus 4. And then and then plus something else. And then in that case, you can have this 1 over 2 split it out. Does it make sense now?
Okay.
Does it make sense? Numerator has to have that gain, whatever it is, 1 over 2 or whatever k is, times exactly the numerator and exactly the denominator, and then plus something else. And then you can split that gain out like this. This gain is this k here.
All right. Makes sense now. Got it.
All right, sure.
Quick question. If k
Yep.
equaled 2, would it be 2 over s then?
You mean which k? This k?
That k.
This k equals 2, then plus 2.
Okay. All right.
Yep. And obviously, the best way is for you guys to find some complicated partial fraction examples. You know the problem, and also you know the result. You know the correct solutions. You know both, and then try them over in the MATLAB. Okay, that's the best way to verify your understanding of the MATLAB result. Okay, you can find that. Due to the time, I'm not able to do it. Not at least today. So maybe you'll see in future if you have enough time to talk about it more. I will upload this MATLAB thing into Canvas as well. And other than that, thank you for attending today's lecture, and see many of you on next Monday. Oh, one last thing, a couple of last thing actually. First, I posted in Canvas exam time survey. Okay, please attend that exam time survey in the Canvas. Okay, it's a part of the module. It's part of the module 2, I think. You have to finish it. You have to submit it. You have a lot of time to do the survey. Ungrade it. It doesn't affect your grades. However, if you don't do it, you are not able to access next and the following modules. Okay, it's something mandatory. Another thing you have to do is the test run exam has been posted. Very easy. The both survey and exam test run are very easy thing for you to do. However, you need to do it. Okay, finish those before you're able to access any following modules materials. Okay. And please check the Canvas for exam time survey and test run exam. All right. Thank you, and talk to you on Monday. Bye now. Sure, no problem. No problem. Sure, absolutely.
Hey,
Thank you,
Dr.
guys.
Zhou.
Yeah.
Could you post the handwritten notes that you have on Canvas?
Post handwritten notes on the
Yeah.
Canvas. To be honest, that's going to
Okay.
be a lot of works for me to do.
Okay, that's fine then.
Is there any trouble for you to access the video, because video containing everything on the notes?
Yep, that's fine.
Do you have any trouble of accessing the video?
Oh no, that's fine. I can look back at the videos. I'll just quickly look back at stuff. If it's a lot of work, no big deal.
And I mean, if you really need the notes in hard copy, well, you can stop by to print some, do some copy thing. But still, it's not as important, as effective as your own handwritten notes. Okay, you got to understand that, because you write it yourself and you copy it. You make a copy from the instructor. It's absolutely different things. Trust me, this. So the thing I still strongly suggest you to write them yourself. Okay. So, but if you really need to print one, well, you can stop by or make a point to stop by. I can provide the copy one from machines. You can have the hard copy ones.
Okay, thanks.
All right, sure,
Yep.
no problem.
I have a question, like where we can see like exam survey. I didn't see any folder or something like that.
No. Here, let me show you. In the Canvas, and then you go to the modules.
Okay.
Can you see it now? Module 2 and the exam survey. Can you see it?
Yes. Oh, it's September 14. Okay.
The test and exam, oh yes. I'm not publishing yet, but I will. I will do.
Oh, okay. Thank you so much.
Sure. It's inside of the modules. Everything go back to the modules. It's not here. Okay, it's not in the menu here. Right?
Oh,
This
okay.
is not. It's not anything here. Go to the modules. Every course materials is in the modules. All right.
All right. Thank you.
Sure, no problem.
I have another quick question. Sorry.
Go ahead, Vincent. It's my office hour anyway, so I don't mind.
Okay, perfect.
Yeah.
The homework assignment that you posted, is that for chapter 1? I just see like number problems or numbers for the problems, and I'm not sure.
Yes. Oh,
Okay.
how to know that exactly? How to know that exactly? You need to go to the syllabus.
Oh,
Let me show you. You see? See it now?
Oh, okay, gotcha.
Module number, homework number, and the chapter textbook chapter number. So it's over there.
Okay.
Right? Yeah, you need details. It's over there.
Okay. Sounds good.
Yep.
Thank you.
Sure, no problem. All right, I will end it now and talk to you guys later. Bye.